We've all been there, right? You're interacting with an AI, and it's incredible. It feels like this genius with the world's knowledge at its fingertips.
Absolutely.
But then the moment the conversation gets a little long, or the task gets complicated,
Yeah.
or you just switch topics, it's gone.
Poof.
It's like having this brilliant colleague who has absolutely zero short-term memory. It's so frustrating.
It really is the classic forgetful genius problem.
Yep.
And, fundamentally just boils down to an engineering constraint we've been fighting with forever.
The context window.
The finite context window.
Right.
LLMs, large language models, they were brilliant at processing information inside that window. But that's it. That's the model's entire short-term memory.
So anything that falls outside that buffer.
Coherence, persistence, consistency,
Yeah.
it all just falls apart.
It's the Achilles heel, even for the biggest, most powerful models out there.
It is.
And this is exactly why those really long horizon tasks, I'm thinking like a software development project that lasts for weeks.
Or a complex scientific inquiry, yeah.
Right, where the agent needs to pull together dozens of different steps and findings. They've always struggled because they run out of tape.
Exactly. So if the core brain, the LLM, is stuck with this transient, fleeting memory, the only logical step is to build it an external one.
An external brain.
A comprehensive, evolving external brain.
And that external brain is the star of our deep dive today. Agent memory.
Precisely. Agent memory is the innovation that fundamentally shifts the LLM from being, well, a passive text generator.
Like a stateless oracle, right?
Yeah.
You ask, it answers the ad.
Exactly, a stateless oracle. And it shifts it to being a dynamic, self-improving learning agent.
Okay, wait, let me just pause on that word because agent gets thrown around so much these days. For our purposes here in this deep dive, what defines an agent?
It's a great question. If you strip away all the jargon, the agent is really defined by its capabilities. It's not just the model.
It's the whole system.
It's the whole system built around the model. So we're talking about an LLM core, plus the ability to reason, to plan its next steps, to use external tools.
Like a code interpreter or a web browser.
Right. And to engage in multi-turn interaction, to perceive its environment, and critically, to maintain and evolve this external memory system we're talking about today.
So an agent is defined by its autonomy and its persistence. And the agent memory is the foundation that actually supports that persistence. It lets the system have an identity and experience that lives outside of one single conversation.
That is the key takeaway. Agent memory is what allows that whole complex system to exist across time and across tasks.
That makes perfect sense. And that brings us right to the mission of this deep dive. We're going to take a really hard look at the recent survey on agent memory systems, the current state of the art.
We're going to unpack the architectural forms these memories take.
The core functions they perform in the real world.
And the dynamic life cycle they operate within.
And you said we have to start with that life cycle.
Yeah.
Why there?
Because it shows you right away why agent memory is so much more than just a simple database. The memory state of an agent is continuously managed. It's actively refined by these operators. It's a living system, not some static archive you just read from.
Okay, let's unpack that then. What does it actually mean to give an AI a memory life cycle that manages itself?
It means we stop just, dumping all the raw data into a log file.
Right.
We give it actual cognitive processes for managing that information overload. So the first operator is formation. When an agent interacts with the world, it's writing code, it's getting tool outputs, it's making a decision, it's producing all this raw, messy data.
Right.
Formation is the process that's highly selective. It transforms those raw artifacts into useful, prioritized memory candidates.
So it's filtering the noise. If an agent writes, say, 100 lines of code, the formation process might decide that only the final function and maybe the test results are actually worth keeping long term.
Exactly.
Because those are the things with potential future utility. It doesn't need to remember every single keystroke.
Precisely. It's selective extraction, and it's based on a prediction of what will be relevant later. That's smart, and it's totally essential for efficiency.
Okay, so that's formation. What's next?
Next up is evolution. So once we have a memory candidate that's been formed, evolution is the process of integrating that new piece of information into the existing memory.
And this is where it gets complicated, I'm guessing.
This is where the complexity happens. It means resolving conflicts if new data contradicts old facts. It means abstracting a series of events into a general skill. And yes, sometimes it means actively and deliberately forgetting old or redundant data that's just causing interference.
So evolution is what turns the raw experience into lasting knowledge.
That's it. It keeps the memory base consistent, generalizable, and efficient.
It sounds like the process that turns specific examples into, like, intuition.
It is. And finally, you have the operational step, retrieval.
Right. Retrieval.
This is the mechanism where the agent builds a task-aware query to pull the relevant memory content from that long-term store
And stick it back into the LLM's context window.
and stick it back in. And crucially, that retrieved memory has to be formatted perfectly. It might be text snippets, a structured JSON, a high-level summary. Retrieval is the bridge between that persistent mind and the momentary thought process.
So if I'm understanding this whole trajectory analogy, the agent loop itself is this dynamic dance between seeing the world and then using its memory to figure out what to do next.
That is the perfect way to visualize it. An execution of the system really just runs along a trajectory. At any given time step, the agent first observes the environment.
Step 1.
Step 2, there's an optional step of memory retrieval. Step 3, the LLM performs its computation or action selection based on everything it has. And then step 4, the action gets executed, which changes the environment, and the loop starts again.
So the memory piece isn't just like tacked on at the end. Retrieval can happen before the agent even thinks, and formation and evolution can happen after.
Absolutely. The memory management, formation, and evolution, it's an integral, flexible part of this loop. You know, you might invoke retrieval continuously for a chatbot that needs to be super fluent.
Okay.
Or for an agent on a really complex multi-stage task, retrieval might only get triggered intermittently, like when it starts a new sub-goal.
And some might just pull a big summary at the very beginning to set the context.
Exactly. The complexity of real agency emerges from these temporal patterns, how often formation, evolution, and retrieval are used across the entire task. So before we dive into the specific architectures, we really need to clear up the conceptual landscape here. Agent memory is a new term, and it gets confused all the time with other more established concepts.
Like RAG.
Like RAG or internal model memory. And this ambiguity creates a lot of confusion, so clarifying how agent memory diverges is essential for you, the listener, to really follow the innovation here.
That's a great place to start. I think for a lot of people, when you talk about LLM memory, their mind immediately goes to the transformer architecture itself. So let's start there. What's the difference between internal and external memory?
Right. Agent memory versus LLM internal memory. So research into LLM internal memory is focused entirely on the intrinsic dynamics of the transformer. This is really technical work.
We're talking about the guts of the model.
The guts. Managing the internal key value cache, or KV cache, which holds the attention history, designing long context mechanisms like Mamba, or using specialized attention sparsity techniques.
So if a research paper is proposing, say, a new way to structure the attention mechanism, or changing how model weights are accessed just to squeeze a few more tokens into the current prompt, that's internal memory.
That's internal memory. You're optimizing the hardware of the brain itself. The goal there is just to reorganize the representational capacity of the model as the input sequence gets longer.
But agent memory doesn't really care about that internal structure, does it?
Not directly. Agent memory is all about furnishing an external memory base that is deliberate and persistent. We care about cross-task continuity and adapting based on what happens in the environment.
It's supporting those explicit operations we just talked about: formation, evolution, retrieval.
Exactly, which are all outside the scope of the model's internal machinery. The internal memory is momentary, the agent memory is enduring.
Okay, that clears it up. The difference between the brain's internal wiring and the agent's external evolving file cabinet. Now let's tackle the big one. RAGE, Retrieval Augmented Generation. RAG has been the workhorse of enterprise AI for years. How does agent memory relate to or differ from RAG?
The relationship is hierarchical. You could say agent memory almost fully subsumes the concepts in RAG. RAG is like the less complex predecessor.
Okay.
Standard RAG takes a static pile of documents, company manuals, internal reports, and it retrieves relevant chunks based on a simple vector search to augment the prompt.
It's basically read-only from the LLM's point of view.
Pretty much. It answers questions based on a fixed set of documents.
So AG is that simple lookup. If I ask my chatbot about our company's Q3 results, it uses RAG to find the Q3 report and summarize it. But the report itself doesn't change because I asked a question.
Correct. Agent memory uses RAG-like retrieval, absolutely, but it elevates the knowledge base from being a static document library to a living, evolving representation of experience. And that is the crucial distinction.
Okay, walk me through an example of how that evolution changes things.
So consider an advanced graph Argate system like those used by ZEP or Memziragang. They structure knowledge not as flat text, but as these rich graphs of nodes and edges capturing complex relationships.
Right.
Standard RAG might just query that graph, but an agent memory system actively constructs, extends, and reorganizes that graph as the agent operates.
So if the agent finishes a complex task successfully?
It doesn't just store the log file, it adds a new node to its graph representing task X was successful using tool Y, and it updates its strategy node for how to approach task X in the future.
Wow. So the agent isn't just querying its knowledge, it's literally building its own experience map in real time. It's forming new memories and relationships constantly.
It's moving from passive data ingestion to active cognitive construction.
And that constructive, self-modifying nature is what separates it from traditional RAG.
Precisely.
Okay, one more comparison. Context engineering. This one can feel almost identical to agent memory in practice, especially when you're dealing with really long conversations or tasks.
It's a subtle but important distinction. Context engineering is best defined as a systematic design methodology. It treats the context window as a finite and constrained computational resource.
So it's about resource management.
It's all about resource management, optimizing the instructions, the state, and the memory payload itself to get the best possible output from the model. This is where you see techniques like token crooning, rolling summaries, and dynamic prompt templates.
Oh, I like that. So context engineering is like packing the perfect suitcase for the LLM's short trip inside the context window.
That's a great analogy.
You've got to fit the instructions, the current state, and the most vital bits of history, making sure nothing essential is left behind, but nothing unnecessary is wasting space.
That's a powerful way to put it. And from that perspective, agent memory is just one variable that needs to be packed efficiently into that suitcase.
So agent memory decides the three most important facts from last week are X, Y, and Z.
And context engineering figures out the most token-efficient way to actually insert X, Y, and Z into the current prompt.
So the two fields converge a lot on practical solutions, like summarization. That serves both the long-term goal of agent memory and the short-term goal of context engineering.
Absolutely. The core difference is really philosophical. Context engineering optimizes the momentary interface. It's about the optimal input right now. Agent memory sustains a persistent, evolving cognitive state that exists beyond any single input.
One optimizes resources, the other models the enduring self.
Two sides of the same coin. One generates the efficient state, the other implements it.
That sets the stage beautifully. We know why we need memory for persistence and how it's managed with that life cycle. So now let's dive into the core architectures. If agent memory is this external active thing, what physical or digital forms does this stored knowledge actually take?
Yeah, the survey organizes this really well into three major architectural forms. And they're defined by where the memory lives and how it's represented. We have token level, parametric, and latent memory.
And each one makes different trade-offs.
Exactly. Trade-offs in auditability, cost, and speed.
Okay, let's start with the one that feels the most intuitive, like a digital diary, token-level memory.
Token-level memory is explicit, it's symbolic, it's discrete, it's memory organized as units. You can actually read text chunks, snippets, structured logs. They're externally visible, and you can access and modify each one individually.
That's the most transparent form.
By far. Which is essential for fields like law or finance, where you absolutely need that traceability. And we can categorize this form based on its structure, moving from a simple 1D log all the way up to complex 3D cognitive architectures.
Okay, starting with the simplest, flat memory, 1D.
Flat memory is just what it sounds like. It stores information as linear sequences or, simple bags of units. There's no explicit modeling of relationships.
So it's just raw dialogue history, a chronological list of events.
Exactly. Or simple user profiles organized by timestamp. A basic memory bank system is a good example. It's like a searchable text file.
What's the appeal then, if it's so simple?
Simplicity and scalability. It's incredibly easy to just append new entries or prune old ones. It scales linearly.
But the drawback must be huge.
It is. The coherence of the agent depends entirely on how good your retrieval is. If an agent needs to connect 3 separate events from days apart, the LLM has to figure out that complex relationship all by itself inside the context window.
Which really limits its ability to do complex compositional reasoning. It can't see the big picture.
It struggles to form those high-level insights, which is why we move from a simple linear log to something that actually encodes relationships. Planar memory 2D.
This is where things like graphs come in.
Exactly. Planar memory introduces an explicit organizational topology, all in a single layer. So units are connected by graphs or trees or tables, encoding things like adjacency, causality, or parent-child order. It provides these pre-baked relationships.
And when you talk about relationships, this is what everyone's calling graph RAs now, right?
Yeah.
Systems like ZEP that build these knowledge graphs from the agent's activities.
That's it. Graph structures are dominant in planar memory because they're fantastic at capturing complex, nonlinear associations. Systems like RAG and LLM, for example, abstract external storage into these addressable triple-based units, effectively acting as a knowledge graph of the agent's own experience.
So the agent can do relational traversal.
Right. It can follow a chain of logic from event A to event B instead of just searching for similar words.
That makes planar memory way more powerful for complex reasoning. If I ask, why did the agent fail step 5? It can actually follow the graph from the failure node back to the tool use node to the initial plan.
That's the strength. And we see this in specialized domains too, like the medical system Huatuo, which uses integrated medical knowledge graphs to inject professional structured knowledge that's easy to navigate.
So what are the trade-offs? It sounds great.
The main trade-offs are construction and search costs. You have to spend a lot of computation building the graph-defining nodes, extracting triples, establishing edges. It's expensive.
Then it's still just one single layer.
Right. Without a higher-level structure, it remains a single monolithic module, which naturally leads us to the most complex form. Hierarchical memory, 3D.
The volumetric, multi-tiered architecture.
Exactly. Hierarchical memory organizes information across multiple layers of abstraction with defined links between the layers. It moves from detailed, raw data at the bottom to compact summaries in the middle, all the way up to high-level thematic patterns or generalized rules at the top.
This sounds exactly like the cognitive structure of a big company. I mean, a CEO doesn't read every single email, right?
Yeah.
They read a summary report, which is based on team summaries, which are based on the raw activity logs.
That is the perfect analogy. You can look at pyramid structures like HiAgent. It manages long tasks by keeping the detailed action logs for whatever the active sub-goal is, the raw emails, so to speak.
Yep.
But it compresses all the sub-goals that are already completed into these higher-level efficient summaries. So when the agent needs historical context, it just retrieves the summary. But if it detects a problem and needs to debug...
It could traverse down to the raw layer for the specific details.
Precisely. Another system, G-Memory, does this with a 3-tier graph focused on insight, query, and interaction.
So the advantage here is massive efficiency in retrieval, but also incredible depth for debugging. It feels like the holy grail. Why isn't everyone using this?
Cost and complexity. I mean, it is incredibly complex to design and maintain that three-dimensional structure. You have to ensure semantic meaning is preserved across all the layers.
And the computational overhead must be huge.
Massive. The overhead for formation and evolution is enormous, which makes it impractical for most real-time deployments without very specialized hardware.
That's a really important point. The choice of architecture isn't about which one is best. It's about fitness for purpose. You're balancing the transparency of token-level memory with efficiency and reasoning power. Okay, moving on from explicit text. Let's talk about the memory that lives inside or next to the model itself, parametric memory.
Right. Parametric memory stores information implicitly within the model's structure. So it's in the weights themselves or in some auxiliary parameter sets. Access is instantaneous, but it's implicit. It happens during the forward pass.
And is this just the model's general knowledge from pre-training, or is it something more specific?
It's specific, and it comes in 2 flavors. The first is internal parametric memory. This is where memory is encoded directly into the original weights, usually through fine-tuning.
So you'd use this to give the agent some large-scale static knowledge.
Exactly. Or persistent priors, like fine-tuning a model to have a specific professional persona, like in character LM, or injecting deep domain knowledge.
The big advantage there is zero inference overhead. The knowledge is just part of the model when it speaks.
Absolutely. The speed is unmatched, but the drawbacks are immense.
It must be nearly impossible to update.
It is. It requires costly retraining, and it's extremely prone to catastrophic forgetting.
Where the new memory just wipes out old knowledge.
Instantly. So it's really only for static knowledge that almost never changes.
So how do we get the benefits of putting memory in the parameters, that speed and deep embedding, without the cost and danger of retraining the whole model?
That's where external parametric memory comes in. The memory is stored in auxiliary parameter sets.
Like LoRa modules or adapters.
Right, they're attached to a frozen base model with these lightweight interfaces.
Hmm.
So systems like K-adapter or Elder inject new task-specific knowledge into these separate modular units.
That sounds like hot swappable memory cards for the LLM.
Yeah.
You load the doctor module for a medical task and then swap in the lawyer module for a legal task.
That's a great way to think about it. It gives you a modular architecture that's very stable. You can update the adapter without ever touching the core model weights, which prevents that catastrophic forgetting.
But the influence is indirect.
It is. The limitation is that its effectiveness depends entirely on how well that adapter interface can modulate the core model's output.
Okay, finally, let's get to the most mysterious and, you said, most efficient form, latent memory. This is memory carried implicitly in the model's hidden states.
It is. It's carried in the model's internal representations, the KV cache, hidden states, latent embeddings. It avoids explicit tokens or dedicated parameters, and it prioritizes efficiency and speed way above human interpretability.
And we classify this based on where the latent state comes from.
Right. We look at its origin: generate, reuse, or transform.
Let's start with generate.
So in the generate approach, auxiliary models synthesize entirely new latent embeddings or tokens. Autocompressor is the classic example here. It doesn't store the raw text of a long conversation.
What does it do?
It summarizes that massive context into just a few dense vectors that the LLM can process very quickly. This enables really high-density compression and, importantly, multimodal alignment.
Meaning you can compress an image or a video into a vector that the LLM understands as a memory.
Exactly. So you pay a computational price up front to generate that compressed memory, but you gain massive efficiency on the back end.
That makes sense. That's a
Yeah.
trade-off. What about reuse? You said that's the simplest form.
It is. You're just propagating the raw internal activations of the model.
Mostly the KV cache.
Mostly KV cache, it offers the highest fidelity because you're preserving the full internal context of the moment that information was created. And it's simple to implement.
But it must scale terribly.
It does. The KV cache grows incredibly fast, which leads to high memory consumption, and you absolutely need efficient indexing to manage that growth. It works for short tasks, but it's unsustainable for long ones.
So the final form, transform, seems designed to fix that scaling problem.
It is. Transform modifies or compresses existing latent states, like the KV cache, using techniques like selection, aggregation, or pruning. Think of a system like Scissorhands, which uses a mechanism to prune tokens it deems low importance.
Or H2O, which retains only specific heavy hitter tokens.
Right. So this approach is more compact and information dense than raw reses, which cuts down on storage and bandwidth. But the crucial trade-off, and it is a big one, is the risk of information loss during that compression.
How do you ever guarantee that the information you pruned wasn't vital for some rare edge case down the line?
You can't, not with 100% certainty, and that's the challenge.
Wow. Okay, so that structural taxonomy token level for transparency, parametric for implicit speed, and latent for efficient state, that gives us a really solid framework. It's clear that building a truly advanced agent is going to require mixing and matching these forms to optimize for different needs.
Absolutely. So now we can shift from what the memory is structured as, its form, to why the agent needs it in the first place, its function.
The architecture is determined by the required function.
Exactly. And we can categorize memory into 3 pillars that map directly to core agent requirements: factual, experiential, and working memory.
Let's start with factual memory. This is the declarative what?
Correct. Factual memory is the agent's declarative knowledge base. Its fundamental purpose is to ensure consistency, coherence, and adaptability. It does this by recalling explicit facts, user preferences, and stable facts about the world. It answers the question, what does the agent know and believe to be true?
And where does this really apply in the real world?
Well, primarily in 2 areas. The first is dialogue coherence and personalization. To maintain a believable persona, an agent has to track user profiles and preferences across different sessions.
So a system like Memory Bank, which builds and maintains a profile of me from our conversations.
Exactly. But the cutting edge is much deeper than just storing facts. Advanced systems like Think and Memory are designed to store inductive thoughts and reflections right alongside the raw text.
Wait, inductive thoughts and reflections. So the agent stores Not just the fact that I like coffee, but it might store a generalized insight like, user expresses a preference for highly caffeinated beverages, which likely correlates with early morning productivity.
That's it, exactly. It's a form of memory abstraction that helps stabilize the agent's understanding of you over very long interactions. This is absolutely essential in sophisticated role-playing agents like Chaturui, which need to maintain a really complex character consistency.
Okay, and the other key application must be knowledge persistence.
Yes, storing reliable world and domain knowledge. In high-stakes contexts, this often means maintaining and querying a knowledge graph.
Like the factual systems we talked about of Watuo, that relies on structured knowledge graphs for factual accuracy.
Right, and this function is critical for something called model editing.
Model editing is fascinating. It lets an agent update a specific fact without needing to be completely retrained from scratch.
Precisely. Methods like MEND or knowledge editor use memory mechanisms to perform these very localized factual updates. This is essential for agents that operate in dynamic fields. Finance, news, science, where information has a really short shelf life.
And this brings us right back to the forms. Why is token-level memory the best choice for factual memory, especially in those high-stakes fields?
It's all about transparency and accountability. Token-level memory is external, it's symbolic, and it supports clear, auditable add, delete, and update operations. If a medical agent makes a factual error, you can trace that decision right back to the exact tokenized memory chunk it retrieved.
You can't get that level of traceability from an implicit or opaque memory form.
You can't, and that's why it's necessary for regulatory compliance.
Okay. Next up, let's move to experiential memory. This feels like the agent's actual learning engine, its procedural knowledge.
It is. It's the procedural learning loop. Its purpose is to enable continual learning and self-evolution by abstracting reusable knowledge from past failures and successes. It answers the question, how does the agent get better at what it does?
So it accumulates history, these episodic traces, and then abstracts them.
Right, into generalizable rules, skills, and strategies.
How does that abstraction actually happen? Are there like formalized levels of this kind of memory?
Yes. The survey identifies 3 distinct levels, and they show a clear progression from raw observation all the way to crystallized capability. First, you have case-based memory. This stores raw, minimally processed interaction histories and specific solutions. Think of systems like Memento or Jarvis One, which store raw, successful survival experiences from the complex, procedural world of Minecraft.
So it's preserving the exact historical episode. When I saw an Enderman at 3 a.m. in the swamp, I used my diamond pickaxe and ran southwest. It's high-fidelity, verifiable evidence.
High fidelity, but also high context cost. Retrieval efficiency and context window consumption are huge bottlenecks here because you're retrieving these large, raw data chunks, which leads to slow and expensive inference.
Which pushes us to the next level, strategy-based memory.
Right, this is where you extract the reusable patterns.
So it's not the specific incident, it's the general approach.
Exactly. Strategy-based memory extracts reusable reasoning patterns, generalized ways to break down tasks, and high-level workflows. Systems like Agent KB or Reasoning Bank distill these general schemas from large batches of success and failure cases. They learn the structure of a good solution.
But it's still abstract. It doesn't give you the actual code to run.
It doesn't. It provides the structural guidelines, which improves robustness on new tasks, but not the executable actions. That's the role of the third and final level, skill-based memory.
This captures the actual executable capabilities.
This is where it gets real. Skill-based memory captures procedural capacity, and it operationalizes strategy into verifiable, callable actions. Things like code snippets, APIs, or specific tool use sequences.
So ToolLM and Voyager are great examples of this. They're constantly building and refining a library of skills.
They are. This form bridges that gap between abstract planning and concrete execution. It makes the agent not just smarter, but actively more capable over time.
So a successful action in Minecraft is the case-based memory. That gets abstracted into a reusable plan, which is strategy-based, and that is finally compiled into a callable function, which is skill-based.
That evolutionary loop is the core of true agency.
Okay, our final functional pillar is working memory. We've talked so much about the context window being limited. Working memory sounds like it's all about turning that limited space into an optimized workspace.
That's a perfect way to put it. Working memory is the active management and manipulation of context within a single ongoing episode. It transforms the passive context window, which is just a read-only buffer, into a controllable, updatable workspace that prioritizes what's relevant right now.
Let's look at the 2 settings here. handling a huge amount of input at once and then maintaining continuity over a long time.
So single-turn working memory handles massive, immediate inputs, long documents, huge code bases, high-dimensional video streams, and it does this mainly through input condensation.
It reduces the physical token count.
Right. A system like LLM Lingua uses perplexity to identify and just discard predictable or irrelevant tokens. It's essentially removing the filler words that don't add much semantic value.
So it's pruning the input before it even hits the LLM, making the prompt shorter, cheaper, and faster.
Yes. And the other technique here is observation abstraction. This transforms raw, high-dimensional data into a concise semantic description.
Can you give me an example?
Think of Synapse, which rewrites a ridiculously complicated HTML DOM tree into a simplified, task-relevant summary for a GUI automation agent. Instead of reading 1,000 lines of raw web code, the agent just reads, "User is on checkout page. Fields required, address, payment info."
That handles the breadth of information. So how does multi-turn working memory handle the length, the continuity over a long task?
The key strategy is state consolidation. You're continuously compressing the stream of history. A system called IR Research, which is designed for scientific discovery, uses an evolving central report as its persistent working memory.
So after every step,
The agent synthesizes all the new information into that single evolving document. This helps mitigate the risk of what you might call context suffocation.
I love that term, context suffocation. It perfectly describes that cognitive load when you're trying to hold on to too much low-value history.
And then there's a more advanced version called hierarchical folding. It's a decompose then consolidate strategy. Systems like HiAgent use subgoals as temporary memory units.
So when a subgoal is finished,
They fold up the detailed log and write back only a high-level summary to the main report. This keeps the active context window small and focused only on the current task.
and finally, cognitive planning ties all this together.
This is where working memory isn't just summarizing the past, it's maintaining an externalized plan or world model that actively guides future actions. The state becomes a forward-looking, structural guide.
So a system like Prime integrates memory retrieval right into its planning loop.
Exactly. And that really helps stabilize performance over those long horizon tasks by making sure memory updates are actively supporting the reasoning steps needed to finish the job.
So we've covered the forms, the architecture, and the functions, the applications. But the part that is truly compelling, as you mentioned at the start, is the dynamics. How the memory actively manages itself, almost like a biological process.
This is where it gets really interesting. Yeah, this is where true autonomy begins.
Let's start with memory evolution.
Memory evolution is that self-refining process. It's all about integrating, updating, and discarding information to keep the knowledge base generalizable, coherent, and, efficient.
First up, consolidation. This sounds like the process of moving short-term experience into long-term intuition.
That's the core concept. Consolidation transforms newly acquired, very detailed episodic traces into structured, generalizable, long-term schemas. The agent reviews its recent experiences. It performs reflection to synthesize connections between isolated events, and then it merges these new insights into its established worldview.
So systems like RMM and Think in Memory are built for this. They store the reflective insights, not just the raw logs.
Exactly. So if an agent encounters a problem once and solves it, consolidation helps it solve the same type of problem faster next time because it has abstracted the key principle.
So learning is cumulative.
It ensures learning is cumulative. But there is a necessary risk here, which is information smoothing. Well, while you're enhancing generalization, you might lose specific, unique exceptions or outlier events. Critical details about a very rare failure might just get lost during the abstraction.
So if the agent abstracts too aggressively, it could lose sensitivity to anomalies that only happen, say, once in 1,000 operations.
Precisely. It mirrors how we function, right?
Right.
We don't remember every detail of every drive to work. We remember the route.
But if there was a one-time critical detour, we might abstract that away as unimportant, only to need that exact information 6 months later.
It is a very delicate balance between stability and plasticity, which brings us to handling factual changes through updating.
Updating revises or replaces memory when there are conflicts or new facts, ensuring everything stays consistent. And this happens in two different theaters.
Yes. The first is external memory update, so modifying your vector databases or knowledge graphs. Early methods would just use destructive replacement. They'd just erase the old fact completely.
Which is bad for historical context and auditing.
Terrible. So more sophisticated systems, like ZEP, introduce temporal annotations. Instead of deleting the old fact, they mark it with an invalid timestamp. This preserves the history, but ensures the agent only retrieves the current valid information.
So the agent doesn't erase its history, it just correctly labels old information as deprecated. That is so much better for debugging.
Much better. And the other theater is model editing, the direct modification of the internal model parameters. Techniques like Roam or Memorial can perform these precise, low-cost corrections to the model's implicit knowledge.
And that's crucial for fixing those persistent factual errors that are just baked into the model without having to do a full, expensive retrain.
Absolutely. And finally, we have the most human-like and maybe the most difficult evolutionary mechanism, forgetting.
The deliberate, strategic removal of information.
Right. Getting rid of outdated, redundant, or low-value information to maintain focus and efficiency. Because if you just let memory accumulate forever, you get increased noise, slower retrieval, and interference during inference.
The agent just gets overloaded.
Exactly. So eviction strategies are mandatory. For instance, the H2O system retains only the most recent tokens, plus any tokens that are identified as heavy hitters, the ones that contribute most to the current task.
But the trade-off here is massive. You need efficiency, but if you prune too aggressively, you risk erasing that one rare but essential piece of knowledge the agent might desperately need later on.
The agent has to learn how to predict future value. It's an incredibly hard problem.
Okay, let's shift to the third pillar of dynamics, memory retrieval. We've optimized the forms and the storage, but if we can't efficiently pull the right information out at the right time, the whole system just collapses.
The retrieval process is almost always the performance bottleneck. The agent has to autonomously decide when to retrieve and what to retrieve, and the first challenge is just automated timing and intent.
How do you program an LLM to know when it doesn't know something?
It's tricky. It requires integrating an explicit self-awareness mechanism. So a system like MemGPT allows the LLM to actually invoke a retrieval function based on its internal state. It decides, my current confidence is low, I need to check my external memory.
So it's a bit more self-aware.
A bit. More advanced approaches use a fast, slow thinking loop. An agent might first generate a quick internal response system 1 thought, and then, if a secondary evaluator agent rates that response as inadequate, it triggers a deeper, slower retrieval and reasoning loop system 2 thought.
That's a huge shift.
Yeah.
We're moving from just passively querying a database to the agent actively deciding it needs more information.
Yeah.
But what about the risk you mentioned earlier?
The risk of silent failure. If the agent overestimates its internal knowledge, if its self-assessment mechanism fails, it won't trigger the retrieval, and those knowledge gaps will lead to hallucinations or incorrect answers without any warning.
It's a failure of internal monitoring.
It is.
So once retrieval is triggered, the agent has to figure out what to search for. This brings us to query construction. Why is transforming the query so important if the user already asked a question?
Because the user's raw input might not align semantically with how the memory is structured. If your memory stores long-term concepts, a short, concrete question might just fail to retrieve the right material. So query construction is like a translation layer.
Between the user's intent and the agent's complex memory index.
Exactly. And there are 2 main techniques here. First is query decomposition. You break a complex query into simpler modular subqueries that you can search for sequentially or in parallel.
So Prime's planner agent does this. It makes a global retrieval plan, then breaks it into smaller steps.
It does. And the other path is query rewriting.
This is where you generate a better query.
Right, to match the memory's structure. The classic example is Heidi hypothetical document embedding. Instead of searching based on the user's short query, the agent first generates a plausible hypothetical answer to the question.
And then it retrieves documents that are similar to that generated answer.
Which makes the query signal much more targeted and effective. It overcomes that mismatch between brief questions and verbose memories.
Okay, finally, we have post-retrieval processing. You've just retrieved a fire hose of potentially noisy, fragmented, redundant memory chunks. You can't just dump all that into the LLM prompt.
You'll overwhelm it, absolutely. This is the crucial final stage that refines the raw fragments to make sure the final context is concise and coherent. The first step is re-ranking and filtering.
Using other LLMs as evaluator.
Right. You use an LLM evaluator or an auxiliary model to estimate the utility of each chunk, remove the irrelevant stuff, and reorder the rest based on relevance. Memento system even uses Q-learning for this, turning memory selection into a learned policy.
And then after we've picked the best pieces, we need aggregation and compression.
This is where you merge those relevant fragments into a single coherent summary. RAG has what it calls an integration agent that identifies relevant historical signals and combines them into an abstract global summary.
So you eliminate redundancy and merge similar information before the LLM ever sees it.
Exactly. You're maximizing the utility of the context window with high-density, pre-digested knowledge.
This detailed look at the dynamics really shows we're not just engineering a better database, we're modeling some really sophisticated cognitive processes. If we connect this to the bigger picture, where does all this research lead? It feels like we're getting closer to replicating the full cycle of human learning and cognition.
What's truly fascinating here is the fundamental shift from simple verbatim retrieval, which is what standard R does, treating memory as an immutable archive, to generative memory.
Okay, what's generative memory?
It's about the agent actively synthesizing entirely new memory representations on demand. It often abstracts or even alters the memory of a past event based on its current context and its current goals.
That sounds exactly like how human memory works, doesn't it?
Yeah.
Our memory is a constructive, imperfect process. We don't replay a video of the past.
We reconstruct it.
We reconstruct the event. And that reconstruction is totally influenced by our current emotional state and beliefs.
Exactly. And this constructive nature leads directly to the next frontier of research. One critical area is offline consolidation. And this is directly inspired by the complementary learning systems theory in neuroscience.
Tell me more about this idea of a sleep-like cycle for an AI.
Future agent systems will likely have these designated periods of sleep where they just decouple from interacting with the world. During this offline phase, they'll rapidly consolidate their short-term, detailed experiences into efficient, generalizable long-term schemas.
And perform active forgetting.
Right. Do active, low-risk forgetting and resolve any memory conflicts they detected during the day. This mechanism is key to resolving that stability-plasticity dilemma, the ability to learn new things quickly without forgetting everything old.
So the agent literally learns while it sleeps, distilling its day's high-fidelity experiences into generalized, efficient intuition, ready for the next day's tasks.
That's the goal. And right alongside these cognitive parallels, we have the massive practical frontier of trustworthy memory. As memory becomes more complex and autonomous, it has to be governed by principles of reliability and accountability.
So what are the pillars of trustworthy memory?
I'd say there are three. First, privacy preservation and access control, ensuring memory is handled with granular permissions and supports necessary redaction.
Okay.
Second, explainability. This means providing traceable access paths and clear causal graphs that show exactly how a specific memory influenced a specific decision.
And third?
Hallucination robustness. This means building in mechanisms for conflict detection, requiring the agent to just abstain from answering when its memory confidence is low, and using things like multi-agent cross-checking to verify facts before committing them to memory.
That makes the shift complete. We started this whole conversation by building a clever external storage system, and now we're moving toward creating a reliable, accountable cognitive architecture that actively manages its own internal state. It's almost like a separate, persistent mind.
So let's wrap this up with the key insights for you, the learner, to carry forward from this. First, agent memory isn't just an optional feature. It is the fundamental engine of agency. It's what separates the LLM, the momentary computation engine, from the persistent, evolving agent, the enduring mind. It's what enables lifelong learning and cross-task consistency.
And key insight number 2. The memory of your AI agent isn't one static hard drive. It's this dynamic hybrid cocktail. It could be explicit, auditable text snippets, the token-level memory for compliance.
Or it could be hardwired, fast-capability parametric memory for instant skill recall.
Or it could be those efficient, hidden computational states, latent memory for context management. The choice of form really dictates what the agent can do and how accountable it is.
And my final takeaway is that the future is self-optimizing memory management. We are moving so rapidly from manually engineered pipelines towards systems where algorithms actually train the agent to learn when to remember, how to abstract experiences into general strategies, and what to forget to maintain peak efficiency.
We began this deep dive by solving the problem of a forgetful LLM by, giving it an external hard drive. We're now heading toward creating agents that don't just archive the past, but actively reconstruct it for future utility. It's a process that really mirrors our own complex, dynamic relationship with history.
And this raises a really important question. If an agent can learn to edit, abstract, and even forget its own history just to optimize its future performance, how do we define the authenticity of its experience or the stability of its identity across different tasks? It's the ultimate cognitive architecture debate, all wrapped up in an engineering challenge.